secrecy and wars, and we had great wars with the C++ people. Before you were born and before there was an internet, we sat around inventing programming languages. The word open source didn't exist. Nobody knew what open source was, so, and everything you did was secret. And then it all changed.
Welcome. I'm Cole from Colorado, and these are the high points of Joe Armstrong's presentation, 26 Years of Erlang, where he looks back at some of the history of the project. Let's hear.
Please join me in welcoming the inventor of Erlang, Joe Armstrong.
26 years ago, what was going on?
I didn't have any grey hairs, and the other people who also developed, I mean, Mike Williams, who met Mike, and Robert, they didn't have any grey hairs either. So one thing that happens if you develop programming languages, you get grey hairs from doing it, and you get one grey hair for every mistake you've made, so that's why I've got quite a few grey hairs.
What came before Erlang?
This lab was just newly formed, and one of the things we wanted to do was to find a programming language that was better than Plex. Because Plex wasn't a really it's a sort of horrible language. Well, I mean, it's very good for its time, but it was like real-time BASIC with parallel processes. So if you imagine basic programs, the basic programs had to be very, 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 very small, but you could have millions of them executing in parallel. Well, not millions, maybe hundreds of thousands. And they each had their own set of protected memory and their own set of registers, and they all ran in parallel. And they ran on this product called an AXD, and they were actually pretty difficult to program.
Already we see in the predecessor of Erlang Plex an emphasis on the isolation of different components of the system. So that's critical in this type of software. What's the scale of telephony at this point?
So, I mean, years before the internet was invented, AT&T and Ericsson had planetary-wide networks running computer-controlled switches.
What languages had an influence on Erlang?
I thought Prologue was really great. And I made an algebra to describe telephony in Prologue. But the only trouble was you could only describe one process. And if they didn't do what you'd expected them to do and you got failure, it didn't work. Right. So then I'd read Tony Hoare's calculus of sequential communicating processes, and I thought, I really like something like CSP, with messages coming in parallel processes, and then Prologue doing the logic. So I was playing with Prologue, and it's really easy in Prologue to write a meta interpreter for another language. So I wrote a meta interpreter for processes in Erlang.
Then there was a critical point in the history of Erlang. Another Ericsson employee, Session Erdling, wanted to prototype a new switch. They didn't want to program in Plex, so they were looking to Erlang. How important was this project for the development of the language?
And I think if it hadn't been for that, there wouldn't have been any Erlang, there wouldn't have been any of this development, because really the test of any theory was basically, can we program this thing? If we can program it, the theory works. If we can't program it, it doesn't. It's very pragmatic.
So what does a telephony system look like?
This is in my history file, and it's a fishbone diagram. And it actually describes telephony. And what you notice, it's not a graph, it's a tree, and it's just describing state transitions.
So Joe was reading the spec for what to do in a three-way call, and he was wondering, well, what happens if right here you hang the phone up? And the spec didn't say, so he asked someone.
He said, well, you ring the phone, it goes ring, ring, you lift the phone up again, and then you're in the same point in the state machine that you were before, so you can do hook 1, hook 2, hook 3. And I said, but that's not in the spec. And he just shrugged his shoulders and said, everybody knows.
So what should happen if something is not specified, if it's not in the spec?
The specification doesn't say what's supposed to happen. And then when you get to this point in the code where you don't know what's going to happen, everybody knows who programs it. And I thought, that's crazy, because I didn't know. And I thought everybody could interpret that differently, and they could make an ad hoc decision. So I thought to myself, well, the only sensible thing to do is crash. We just crash this call because we don't know what to do.
How is a call like a file?
In a file system, if a program opens a file and does something and then crashes, the operating system closes the file for you. It's not still open, and then you can use it again later. So I thought to myself, well, a call is like a file. So what happens if you do this hook flat on hook? You crash the program, somebody else will watch, the operating system will watch, and it will close the call, just like closing a file, and it will just put everything to rights.
So this is a common pattern used in Erlang, a worker process that tries to accomplish work but may crash if it encounters bad conditions, and then a management process that will clean up after the worker. And that's a very common layout.
And that was the origin of this thing that now I call let it crash. But what you do is you say you do not program the abnormal things, and you do not make any decisions about how to program the stuff that's outside the specification. What you do is you crash your program, you let somebody else observe it, and put back these invariants. And I thought that's the only sensible way to program.
At this point, Robert joined the project.
Robert Bearding then joined me, and Robert always sort of works the same way. He always starts off with him saying, "Do you mind if I modify your program a little bit?" And then a few months later, or a few weeks later, none of your program is left. And there's a comment at the start that said Joe wrote the original version, but then there's absolutely no lines of code left, and then Robert's rewritten. And then I'd rewrite what he wrote, and we swapped backwards and forwards like this.
How long did a rewrite take?
It took 4 days to rewrite all of Erlang. Right, the entire system took a 4 day to rewrite it. And because there's only me doing it, and Robert had joined it.
How powerful were these computers you were programming?
This machine wasn't big. This was a VAX 11750 with maybe a couple of megabytes of memory. So it's as I say, this like my little mobile phone. This machine is 20 million or 20 to 100 million times more powerful than the machine that we developed Airline on.
You were trying to build the switch. What were your plans? What were your goals?
We kind of split into two groups. They were going to make the product, and we were going to speed up Airline by a factor 70.
Ambitious. So you needed to teach a bunch of people Erlang programming. A bunch of people needed to become Erlang programmers for the first time. How did you teach people?
And we developed courses because people wanted to learn Erlang. Because at that time, Erlang wasn't really developed, and you actually had to know quite a bit of prologue to program it, because the control logic was in Erlang, but when you did computations, it was in prologue. So you also had to learn prologue. So made the first prologue course. There we go. And here's the slides from the first prologue course. This is before PowerPoint. I'm not very good at drawing.
What did the documentation look like?
So this is the entire documentation for Erlang version 1.05. That is it. That's the total documentation.
How's performance?
Well, performance was poor, and it's a kind of we played a lot. So first of all, this is Erlang. This is the number of Erlang reductions per second against time, and around about 1987, 1988, it's running at 300 reductions per second.
What other implementation strategies did you explore?
Attempt was to compile it into a programming language called Strand. Strand was a concurrent logic programming language. And that was when I made a mistake, which I never made again, actually, and that was telling people the result of a performance measurement that will happen when you've written the program without actually writing the program. So we said, well, when we've written the program, it's going to go 20 times faster, we told everybody with great confidence. Although we'd never written the first, I will never, ever make any statement about performance that is not based on measurement.
Why is predicting performance challenging?
There's no algebra there. If A takes time t1 and B takes time t2, if you do A followed by B, is it going to take time t1 plus t2? Nobody in the planet has. There's no algebra for that. Nobody's got a clue. It might be faster, it might be slower. Who knows?
So Joe said about implementing his own abstract machine. How'd you start?
Robert had collected a whole bundle of papers on how things like the Warren Abstract Machine worked and the Strand virtual machine worked, and he collected all these papers. He hadn't read them, but he collected them all and put them in a file. And I remember I borrowed this file and took it home one weekend, and I read every single paper from beginning to end. And I understood nothing. And it was just a complete, I don't understand anything of this. And then I spent, I think on Monday morning I went into work, and suddenly I went, oh! And I understood it. Something happens in your brain, there's this, take information in and try to understand it. You don't understand it, and then go to sleep and things. Your brain rearranges the information you fed. And the thing is, all these different papers, they were all doing the same thing, and I'd misunderstood what it was.
This is very similar to something Rich has talked about in Hammock Development, where your brain maybe needs a little bit of time and rest to absorb something. You'll seem at first like you can't understand it, but given a little bit of time, suddenly you can understand it. And it's pretty amazing what humans can learn when they put their attention towards something. So what did you build, Joe?
Then, as a basis of that, built this thing, the Jam, which was Joe's abstract machine.
Now we know that processes are really important to Erlang. So how are processes modeled in the Jam?
Every process has got a stack and a heap and a set of registers, okay? The registers aren't real registers, they're just an area of memory. And the stack and heap have got a couple of pointers into them. Everybody knows what stacks and heaps are, yeah? Right.
For the group of Erlang programmers he was speaking to, that was true, but for anybody who doesn't know, a stack is keeping track of what the program is in the middle of doing. So you might be in the middle of doing laundry, and then you're in the middle of folding your blue shirt, and so the stack is keeping track of the various things that you're in the middle of doing. And the heap is for storing information where you are not quite sure how long you'll need it, and it's not tied to what you're doing as part of the stack. So give us some details. How was this programmed?
Ask yourself, what does that look like in memory? Okay? So it's got to be put into a 32-bit machine containing tag pointers. And we take about, say, 5 or 6 bits for the tag, and the rest of the word is a pointer. Okay, so a tag tuple has a tag that says T, I'm a tuple, and it points to the heap. And on the heap contains words containing tab tuples, and the first one says it's got an arity tag, A. I say, I'm an arity tag, and I say, whoa, I've got 3 things in my tuple, okay, because a tuple with 3 things in. And the first thing is a rectangle, so it's got an atom tag, and it points into the atom table, okay? And I is an integer, it's a direct integer, so it's 10, and I is that. So that's how it looks in memory. And it's still like that today.
So that's a peek into how some of the data is stored in the abstract machine. How about programs? How do you represent a program in the Jam?
What instructions do we need to emit to create a tuple with 3 elements in? I say, let's just invent a language. This is all what it's all about. So here, I'll make 3 instructions. Push int 20, push int 10, push atom rectangle. Now you've got 3 things on the stack. And the final instruction is make tuple 3. And what does that do? It says, remove the top 3 entries on the stack, put them on the heap, and replace the top entry on the stack with a pointer into the heap. Then the compiled code for that is going to look like enter foo 0, enter the function foo with 0 arguments, do this push atom ABC, push int 10, make tuple 2, and return. Really simple. It's about the simplest code you can imagine. If you take those 2 instructions, turn them into a byte-coded machine. Push int means the bytecode 16. 10 is a 10, it's an immediate integer. Make tuple is the bytecode 20. Make tuple 2 is like that. And then you write the C. So it says, it's just a switch statement, and it says switch case 16, push a short int onto the stack. stop++ is baked into PC star ++ break. That's it. It's no more complicated than that. That was the Jam.
You were implementing the jam in C. Were you an experienced C programmer?
So I started writing C. Now, I am the world's worst C programmer. Anyway, so I wrote this, and then Mike Williams came along and declared my C to be the worst C ever seen on this planet. And so he rewrote this, and that was the. Now the team is up to 3.
So with a team of 3, how'd you divide up the work?
We kind of split the work up. I wrote the compiler and the virtual machine, sort of designed it. Mike implemented the virtual machine in C, and Robert wrote all the libraries.
How'd you tell the story of Erlang internally to the company, promoting it to other people? What did that look like?
This is the original Erlang movie, which was actually made for ISS 90. Right. No grey hairs.
Hello, my name is Bjarne Dekker, and this application is based on telephony. It communicates with the Sun workstation, and the Erlang programs we are going to be running are actually running on that Sun workstation.
We have an Erlang interpreter window here and an Emacs editor window here. What we see here is a symbolic trace of the communications to and from the number analyzer. Port 67, which signifies a hardware address of a telephone.
Okay, I'm now going to leave this call set up from this phone here, and I'm going to make another phone call to Joe on his other telephone. Hello, Joe.
Hello, Mike.
Hello, Robert.
Hello, Mike. We see here that something has gone wrong. An error has recurred. We will try and correct it, save the file, and load it again into Erlang and see if it works.
Let's see if Robert succeeded in fixing the error. I'll do the same thing again. First, I'll make a call to Joe. Hello, Joe.
Hello, Mike. Hello, Robert.
Hello, Joe. Hello, Mike.
Hello. Well, it worked this time.
I think you managed to fix the bug then.
Yes, finally.
Do you remember before we went into conference, we set up a call? Well, let's see if that call is still running.
Well, what you've seen now is that this call was totally undisturbed by the fact that we have had an error in the system in other calls, that we've reloaded parts of the system software. This call here still worked. Calls in this system are completely independent of each other. An error in one call will never affect the correct operation of other calls. Erlang programs are concise and elegant. In fact, they are about 7 times shorter than equivalent programs written in C. It's easy to write robust systems in Airline. And of course, all this leads to very short lead times.
And we wanted to demonstrate the idea of concurrency to the guy in the street who could, it's a software idea. So we thought, I know what we'll do. We'll get one program to control both a train set and a telephone exchange. Because then they'll understand concurrency. Well, actually, it wasn't quite true. It didn't really have anything to do with the man in the street understanding. Robert wanted to buy a train set with money from the lab. And this was one of the first Airline courses, and it was an incredibly popular course.
Did you need anything special to program trains in Erlang?
At this stage, floating point numbers came into Erlang in order to compute the graphics needed for the trains. That's why we've got floating point numbers.
And the number of Erlang programmers grew. They had a conference.
We had the first Erlang conferences. Here's the first Erlang conference. Everybody got an Erlang hat, and this was limited to the number of people who fit in this room, because this was the room we could get for free, and there were 80 people who could fit into the room.
Let's see some promotional materials.
This is early promotional stuff, blindingly fast. You know, many people think that modern programming language like Prologue and Erlang are slow. Nothing could be further. Sorry? Yes. Praise from a convert. After years of struggling with D++, a first-time Erlang user and convert from D++, Peter programmer said, I just can't believe it, said Peter. What I estimated to take 6 months to write in C++ took only 10 minutes to write in Erlang. Amazing but true. You know, and so we published this stuff, and oh, we had great fun.
What events profoundly affected the history of Erlang that maybe you didn't plan?
And then the first of two major events happened. Two events have really dominated the reasons why Erlang sort of came out of Ericsson. And none of these were in our control. The first major event was that on the 8th of December 1995, the AXEN project was cancelled. Now, the AXEN project was a very large project that was taking place in the same building. It had run for 7 years, and at its height had over 1,000 people working on it, and had burnt many thousands of man-years of work. And it was to build the ends of the new AXEN, the new system of the future. And on the 8th of December, they gave up. And what they'd actually built at that time was some pretty good hardware, which couldn't be controlled by software. It actually crashed. It was written in C++ and used an amazing design system that they'd made. And it crashed after 6 calls went into it, which wasn't very good. Now, we had actually programmed the same hardware in Erlang just for fun, although there was an enormous amount of opposition to prevent us from doing so. And so our stuff was kind of ticking along and doing hundreds of calls and didn't crash. And it was only written by 3 or 4 people. And this was what I call wars.
I can't imagine wars or opposition. Why wouldn't anyone be happy to have these technologies merging?
We weren't very modest in those days. But this is kind of youthful enthusiasm. You know, programmers, they write some code and they want to show it to everybody and think, oh, it's great fun. And they don't think that, you know, you're a programmer, you've just written what 100 C++ programmers have failed to do. You want to show it to people because you're quite pleased. And you think they're going to be pleased. Well, they're not. Of course they're not. No. Who wants to be a boss of one sort of pain in the arse Erlang programmer? Or do you want to be boss of sort of 100 C++ programmers? Your salary depends upon the number of people you're boss over.
Okay.
Following the collapse of the AXEN project, they sort of branded it, and they said, well, let's do it all again. We'll keep all the hardware, and we'll do the software in Erlang. And that was the first golden period, really, because up to that stage, there was no backing from the company to do anything. It was a lab thing.
He goes on to explain it was used for smaller things, nothing of this scale before.
In 1998, 2 years later, the AXD 301 was produced. This is a scalable backbone switch, scaled to slowest speed, I think, is 10 gigabits per second or 16 gigabits per second, and it scales from 10 gigabits per second to 160 gigabits per second. It's used by, say, British Telecom in the backbone of British Internet for British Telecom. The only trouble with that is because it will switch up to 160 gigabits per second, about, you know, for a country the size of Sweden, you can only sell one. And and I think British Telecom bought 3 or something. So I would view it as a great technical success, but it didn't earn any money because it was so bloody powerful that nobody, you only need to buy one. You know, America might buy 10 or something like that, but I mean, you're only selling a few of them.
Success sounds good.
This was a great success. And so then, as a sort of thank you for it being a great success, we were banned.
Ericsson had decided internal projects moving forward would all be programmed in Java and C++. So not Erlang, not other things. And so Erlang was effectively banned for future product development. At this point, Erlang started to look towards a future outside of the company. So this must have been tough news for the language developers. How did they tell people?
And it all turned out very strangely. That's why this slide ends here. Because just before I was banned, I was invited to give a keynote speech at ICFP, the International Conference on Functional Programming, and I prepared this slide, and then we were banned. Right. And so I stopped the slide at the point where we were banned. And I gave this talk about Erlang, and we didn't know what to say, because Erlang was being promoted in the ICFP as the poster child of functional languages. And if I were to go there and say that Ericsson itself didn't believe in it and had pulled the carpet from under its feet, it would have kind of destroyed the credibility of that message, you see. So although we were banned, you see, it wasn't open source, so nobody knew about this, right, apart from us who were really pissed off. And so I gave this talk and things and everything, and I just kind of, the one fact that I just kind of forgot to mention was that it was banned.
How did this lead to open source?
I talked to a management consultant. He said, oh, banning stuff's always interesting, it's good. Because what happens is like a flower. If you take a flower and you smash your fist into it, then the things kind of splatter out into the ground and they start growing again. And you're losing control now because these things start growing and things start happening. So one of the things that happened as a consequence of that was open source Erlang.
And then a few days after Erlang was open sourced.
And so all the guys who'd done Erlang, apart from Mike, left Ericsson and formed a company called Bluetail. And this was 1998, where venture capital was extremely easy to get. How much money do you want? And we thought, hang on, but we don't know. We hadn't thought about that. No business plan, no sort of calculations or anything. And he just said, how much money do you want? We thought that for 5 million kroner, about $800,000 or something. And then he said, I can't get it this afternoon. Is tomorrow all right?
This must have been a stressful period. How did it work out?
When Erlang was banned, I couldn't sleep at night, and I thought I was going to get ulcers, and I was worried about it, and all these things happened. But the consequence of that were the open source Erlang and Bluetail. And we sold Bluetail 20 months later for $154 million. So it was kind of okay.
Once it was open source, did people pick it up?
One of the big questions we never knew is Erlang going to seed? And we knew if we taught it to people. I've taught hundreds and hundreds of people Erlang. We knew that if I taught them Erlang, or Robert taught them Erlang, that the students understood it. What we didn't know was if people who we had never met could teach it from the books and things, and if it could spread without our influence there. And we discovered to our great amazement that it could, and it began to self-seed. 10 years later, there's all this stuff, there's books and there's things and there's all these companies and they're some of them are pretty big and
How would you describe the spread of Erlang?
And so what happened with Gutenberg was that the guys who Gutenberg taught to do printing formed their own print shops and spread off and did that. That's what's happened with Erlang, you see, because what we had was the original lab, and it's like the DNA of Erlang. So the DNA of Erlang, it's spread from the lab into Bluetail, okay? And then Bluetail lasted for 2 or 3 years, and it split off, and then its DNA moved into 2 companies in Sweden, TLF and Klarna.
Any activity from the academic side?
Francesco Sarrini, the kind of key figure here, he learned Erlang at the University of Uppsala as a student, and he wanted to do a master's thesis. And he really liked Erlang. So he phoned me up one day and asked if he could come and do a master's thesis, and I could supervise it. And he came along, and I supervised his master's thesis. And then Francesco formed Erlang Solutions. I mean, I've had great fun in all this time. I've worked sort of in labs, in Ericsson, in the lab, and I've had a startup, and I've been an academic. I got a PhD and done some research and stuff. And it's really nice, kind of, that's how I got my grey hairs, it's kind of fun. And I really like to see this whole picture. Thank you.
Thanks, Joe. Welcome. Hello, I'm Cole from Colorado. No, nix that. Okay.